The overall objective of this work was to develop proof of concept data to show that a novel reactive electrochemical membrane technology is a viable option for the removal of PFASs from investigation-derived waste samples generated from groundwater sampling. Specific technical objectives associated with the work include development of reactive electrochemical membranes for destructive PFAS removal in synthetic and real groundwater samples, determination of the optimal operational mode, and calculation of energy requirements for the REM-based system. A specific focus on treatment of PFAS and PFOA was made, which allowed comparison of results to existing literature. The oxidation of PFOA and PFAS in synthetic solutions indicated that approximately 5 log removal of PFOA and PFAS was achieved in a single pass through the reactive electrochemical membrane, with a hydraulic residence time of only 11 seconds and at applied potentials of 3.3 volts versus the standard hydrogen electrode for PFOA and 3.6 volts versus the standard hydrogen electrode for PFAS. Permeate concentrations were below the analytical detection limits of 86 nanograms per liter for PFOA and 35 nanograms per liter for PFAS from initial concentrations on the order of 5 milligrams per liter. The energy consumption per log removal to remove PFOA and PFAS to below the detection limits were 5.1 kilowatt hour per cubic meter and 6.7 kilowatt hour per cubic meter, respectively. In addition, non-normalized observed reaction rate constants for this data were calculated as 607 per hour for PFOA and 210 per hour for PFAS. These values are more than 2 orders of magnitude higher than those reported by other destructive technologies such as ultrasonication, photocatalysis, vacuum UV photolysis, and microwave hydrothermal decomposition. Additional work involving real groundwater samples were also conducted. Results showed that single-pass flow-through mode could only achieve approximately 50% PFAS destruction, which was attributed to background organic constituents and low solution conductivity. However, operating in a recycle mode with high permeate fluxes achieved greater than 99% destruction of the total measured PFASs, with individual concentrations less than 60 nanograms per liter. Recycle mode required a total energy consumption of only 2.9 kilowatt hours per cubic meter per log removal, which was significantly lower than other destructive technologies. The high rate constants reported in this study are the highest reported for electrochemical oxidation of PFASs, and the low energy consumption are much more favorable than other destructive treatment technologies, demonstrating the promise of the reactive electrochemical membrane technology for PFAS